To finish off our unit on electric potential, okay, we will cover the following three topics in part 3 of this presentation. First, we'll talk about the potential energy of a discrete charge distribution, how to calculate it, of course. Secondly, we'll explore how to calculate electric fields when the electric potential is known or given to us. And lastly, we'll talk about properties of what we call equipotential surfaces and look specifically at the case of the charged conductor that we introduced previously, since, as we'll soon see, a charged conductor is an equipotential surface. So in this slide and the next, let's start by talking about how to calculate the electric or electrostatic potential energy, okay, of a discrete charge distribution. And here you have to imagine that, remember, when we define potential energy, we define it in terms of work. We say that it is the opposite of the work done by a conservative force on an object, in our case, a charge, okay, assembling this group of charges, or it is equal to the positive of, let's say, the work done by an applied force against the conservative force, okay, in our case, in order to assemble this charge distribution. So I want you to imagine that you inhabit a universe, okay, where there are no charges, and we're going to, one at a time, okay, build the charge distribution. And in this example we'll look at an example with enough charges that hopefully you're going to get the idea of how this works. Okay, on the next slide we will, okay, generalize our results here. But okay, we need to start by finding the amount of work required to assemble a charge distribution consisting of 4 charges. Okay, and so when we have no charge in our universe, to bring in that first charge requires no work. Okay, it is not experiencing a force or field due to any other charges, since it's the first charge we introduce into our universe. Therefore, okay, the work required to bring that first charge in is 0. So let's assume that we want to bring our first charge Q1 into this position here, P1, which is a distance R1 from our origin. And as we said, that first charge requires no work, okay, to bring it in from, let's say, infinity to point P1, okay, since there's no other charge present, okay, to exert a force on it. So, okay, to bring in the second charge, however, to some point, well, that is going to require work, whether it be positive or negative, depending on the sign of our charges. Why? Because to bring in that second charge, okay, it will experience the electric potential, okay, due to that first charge. So, you know, that requires us to exert some type of force to bring it into position. So let's suppose that we want to bring in our second charge Q2 over here to point P2, which is a distance R2 from the origin of our coordinate system. Well, okay, here, that second charge Q2 is going to experience the potential, okay, an electric potential, I'll call it V2, at that point due to charge 1. Notice that, okay, the potential V2, it's a potential at point 2 due to charge 1. So basically that's why we would say that, okay, that potential, okay, is equal to K times Q1, the charge of point charge 1, times what I call R12, where I'll say in general R sub ij represents the distance between the ith and the jth particle. So that's simply the distance between point 1 and point 2. If that is the electric potential at point 2 due to charge 1, then to bring in the charge, okay, having a size Q2 there, well, we know that the work is simply, okay, the charge times the potential. So we must do an amount of work W2 to bring charge Q2 into that point. Okay, we'll say is Q2 times V2, where remember V2, that is the potential due to charge 1. Okay, so Substituting, we know our expression for V2 here, multiply it by Q2, and here we have our expression for the amount of work done. Now, to bring in the third charge into our universe, well, it's going to experience a potential due to charge 1 as well as a potential due to charge 2. So, okay, we're going to have to do work, okay, to overcome, okay, the field or the forces due to both of those other charges. So here, to bring in charge Q3 to point 3, okay, distance R3 from the origin, like we say, okay, it's going to be equal to Q3 times V3, where V3 is the electric potential due to the other charges, Q1 and Q2. Let's start by calculating V3, okay? So the potential here at point 3 before we bring in charge Q3 is just the potential due to charge 1 at this point plus the potential due to charge 2, okay? And that's why we use this notation. So K Q1 times R13, that's the distance between point 1 and point 3, plus K times Q2 times R23, the distance between point 2 and point 3. So once we know what the potential looks like at point 3, multiplying the potential there times the charge Q3 gives us an expression for the amount of work done. I think you're getting the hang of this here. Okay, the last charge to bring in charge Q4, well, it will experience, okay, the electric potential due to charges Q1, Q2, Q3. So let's start by figuring out the potential at point 4 here, okay, due to charges Q1, Q2, Q3, and then we'll figure out the work done to bring in that fourth charge. So V4, notice here, is KQ1 times R14, divided by R14, plus K times Q2 divided by R24, plus K times Q3 divided by R34. Each of these terms is the potential of a point charge, okay, and the distance we're looking at is the distance between the point we're bringing our new charge to, okay, and each of these other point charges. So once we know V4, we will multiply by Q4 to find the total amount of work done. So here we have it, okay, the work to bring the fourth charge in Q4 is what we get by multiplying Q4, okay, the amount of that charge by the potential at point 4, which we figured out to be V4. It looks like this. So now the total amount of work done, as you would imagine, is what we get by adding up, okay, the total work due to each of these work terms. That is W1 plus W2 plus W3 plus W4, which we will do on the next slide. Remember now that the total electric or electrostatic potential energy of the charge distribution is exactly equal or identical to the amount of work that is required to assemble the charge distribution. So what we found on the previous slide was the work required to bring in each charge, each of those 4 charges, one at a time. And if we sum up all of those work terms, now we have an expression for the total electrostatic potential energy that exists, okay, in such a charge distribution. So here goes. We had these 4 work terms. You recall that, okay, it took no work to bring in the first charge Q1, that's why that's 0. To bring in the second charge required just this amount of work, right? Okay, to bring in that third charge, okay, required this amount of work here. Okay, we had 2 work terms, and to bring in that fourth charge, okay, we had to do work against charges 1, charges 2, and charges 3. So we add this all up and we have the total electric potential energy of this charge distribution. Now, a very important case of this is just, okay, the electric potential energy of a combination of 2-point charges. Well, that's what you would get if you stopped the process right here. No work to bring in the first charge, okay, only work to bring in that second charge due to the first charge's presence. Okay, therefore we have, for a collection of 2-point charges, the total potential energy, okay, has a single term here. So this is quite useful to know. Just want to point out here that potential energy, Okay, unlike field, okay, doesn't go like distance squared, it goes like distance to the first power. If we want to generalize our discussion here, what if you had endpoint charges? Okay, could we figure out a way to write this very succinctly? Well, yes, with this new notation that we introduced here. So the electrostatic potential energy for endpoint charges, we can use our summation notation here. We can write it like this. Okay, we can sum over these indices I and j, okay, all the way up to the case of endpoint charges, whatever that is. In our example, we had a value of 4, right? We had 4-point charges. Notice here that I does not equal j, so we sum over all possibilities of Rij where I does not equal j, because that would, the distance between, okay, a point charge in itself would be 0. Okay, that would cause us to blow up. So you kind of see here that when we look at this, okay, for the case of 4 charges, if n is equal to 4, we have to look at all permutations, all combinations from 1 to 4, okay, where we do not let I equal j. So starting with 1, okay, we have, okay, case 1, 1 doesn't work. That's where I equals j. We have 1, 2, okay, 1, 3, and 1, 4. Okay, when we go to our next number in our index 2, okay, we don't have 2, 2, okay, and I will say 2, 1 and 1, 2 are the same distance, right? So we really have 2, 3 and 2, 4. Okay, and then finally, okay, when we look at 3, okay, the next number in our index, okay, the next permutation, okay, while 3, 1 and 1, 3 are the same, okay, 3, 2 and 2, 3 are the same. We've already included that. 3, 3 makes no contribution, so we end up with 3, 4. So you kind of see here when, okay, the order that we write these indices doesn't matter. In other words, R sub 1, 2 and R sub 2, 1 are identical, so we would not include those terms twice. Okay, so here we have, okay, like I'm saying, we will sum over all pairs of ij where I is not equal to j, since that would require that R sub ij equals 0. Okay. So we've talked about how to calculate the electric potential difference and the electric potential from the electric field if the form of the electric field is known. Okay, this comes from the definition of electric potential difference. Can we do the opposite? That is, okay, given the electric potential, if we start out by knowing that, can we calculate the electric field from that? Well, let's listen to the advice of this one-eared rabbit. Okay, he never steers us wrong, right? When Bongo tells us that in calculating the electric potential from the electric field, this is accomplished through integration. Okay, you see the definition there that you know, love, and are very familiar with by now. Okay, then can you predict how the electric field can be calculated from the electric potential? Okay, well, let's take a look here. If the electric potential and the electric potential difference is defined to be the integral, okay, of an expression incorporating the electric field, okay, then perhaps, okay, going the opposite way, according to what we know about calculus, we would be differentiating. Let's see how this works out in theory. Okay, we have said previously that, okay, when we're looking at a continuous charge distribution, that the contribution, okay, to the electric potential from a charge element dq, however we break up that charge distribution, okay, that infinitesimal contribution dv, okay, was described as minus okay, the dot product of the field and that displacement vector ds. And then remember, by summing up the dVs or integrating, we got the total potential. Okay, but if we just look at that integrand here, if we just look at dV, let's look at that, and using the definition of the dot product, okay, let's expand it here. So magnitude of V times the magnitude of ds times the cosine of the angle between them, which we can, okay, write like this, right? Okay, when you multiply expressions, it doesn't matter what order you multiply them together in. Okay, so minus e ds cosine theta we can, okay, write as minus e cosine theta ds. And the reason we would do that is, remember what this is, okay, in our dot product. Okay, e cosine theta, that is really the projection of the vector e onto our second vector ds. So it is really the component of the electric field in the direction of the displacement. That's simply the definition of the dot product here. So here, if dV is the infinitesimal, okay, difference in potential between 2 points in space, a distance ds apart, and what we're saying here is that, okay, when you look at the projection of, okay, E onto ds, okay, that is how we can interpret E cosine theta. So we will say that, okay, we can write the projection of the field onto ds, we'll write that as E sub s, okay, that is simply E cosine theta, okay, here where E sub s is the field component in the direction of ds, the projection of E onto ds. And if we rearrange differentials here, okay, looking at this expression, we see here that E sub s is simply minus dV ds. All right, so there we have it. Okay, we see that, okay, the S component of the field is what we get by taking the opposite of the derivative of electric potential with respect to that coordinate S, that spatial coordinate S. So the coordinate system that we very often use in this class here is a Cartesian coordinate system. So let's translate, okay, this general expression here to, for this particular coordinate system here. We can say then that, and you'll notice here that I'm going from ordinary derivatives to partial derivatives. If the electric field is a multivariable function, okay, if it is a function of x, y, and or z, then we need to, okay, take the partial derivative as opposed to the ordinary derivative. So what I'm saying here is that the x component of the electric field is what we get by taking the opposite of the partial derivative of v with respect to the coordinate x. Similarly for y, the y component is the opposite of, okay, partial v with respect to y, and so on. And we can write this in terms of our unit vectors I, J, and K, and say that the total field then is, okay, what we get by adding up, okay, the electric field for each of the components, okay, to form the total field here. And look, another very common symmetry that we have is radial symmetry, in which case we can, for a spherically symmetric charge distribution, we can say that the electric field, so that well, okay, dV, the infinitesimal contribution of the field to the potential, we can write, instead of minus E sub s ds, we'll write as E sub r dr, okay, where we have this radial symmetry, which, okay, we can then write the field, okay, which for this radial symmetry has only one variable, one spatial coordinate to represent it. That is, okay, the r direction or radial direction, in which case that single component of the field here, E sub r, is what we get by taking the opposite of, okay, the derivative potential with respect to r. I could here probably evaluate this as an ordinary derivative, okay, if it is if the potential is expressed only in terms of r. To be general though, if you have a multivariable function for the potential, you need to take partial derivatives, okay, to be complete with your definition here. So let's look at an example where we apply this new approach. And what we're going to do is we're going to take the example of the charged ring. Since we found the electric potential along the axis of a uniformly charged ring in part 2 of our unit on electric potential, okay, last time, we're going to start there. Okay, we're then going to differentiate it to be able to derive the expression for the electric field. And you recall that in week 2 of the course, after we talked about Coulomb's law, we derived an expression for the electric field of the uniformly charged ring. So we can compare our answer, and as we know, they should match, right, if this theory really works. So in this case here, we see the picture of the charged ring. Okay, here's the expression we derived last time for the electric potential at a point, an arbitrary point P along the axis of the ring. Okay, for any particular problem, you know, X will be defined, but in general, X could be anything. So to be general here, it should represent a variable. Okay, and we said then that the electric field, okay, is what we get by differentiating the potential with respect to any spatial coordinates, right? We got to take the partial derivative. Well, the only spatial coordinate here is x, and of course we've got to take the opposite of that. So when we take the partial derivative of our expression here, okay, with respect to x, okay, then we should have this expression for the x component of the electric field there. Now, here we will just, this is a polynomial function here. We're going to write it, instead of with the square root in the denominator, let's write it as a power here. We'll bring the negative exponent, sorry, the exponent of the denominator up to the numerator, okay, making it negative here. And you know, when you find the derivative here, okay, for a polynomial function, you know, we're going to take our exponent, negative 1/2, multiply through, okay, by the argument, okay, then subtract a 1 from the exponent, that gets us to negative 3/2, and then of course we have to, okay, take the derivative of the argument here, which is 2x, and once we simplify this here, we find out that, okay, this looks here exactly like, okay, the expression we derived way back in week 2. Notice that there is no, when we differentiate with respect to y, there is no y coordinate, so the derivative is 0, and the same applies, okay, for the z coordinate as well. So here we have it, okay, the x component of the electric field, okay, the only component of the electric field matches what we derived previously. So this approach works, right? To go from field to potential, we have to integrate. To go from potential to field, we have to differentiate. In this case, partial differentiate. And don't forget, in both cases, you've got that negative sign. As I mentioned in the opening slide, the last topic that we're going to take a look at in our unit on electric potential is the electric potential of charged conductors and what we call equipotential surfaces. So to introduce this topic, I want to show you, okay, some equipotential surfaces for the human body. And if I were to ask you, you know, well, what is being shown in this diagram here? What you're seeing is lines. The lines that you're observing here are lines of constant electric potential, okay, on the surface of the human body. Where do these electric potential lines come from? Well, as you might guess, okay, the beating human heart. Okay, it turns out that the beating human heart, when you look at the two chambers, it behaves exactly as an electric dipole here, okay, which we're now very familiar with. So as you see in the picture here, okay, these lines that you see here are what we call equipotential surfaces. And as we'll see today, they're very similar to the contour lines you would see on a contour map. Okay, if you have ever looked at a topographical map for which you could use, you know, when you're backpacking. in the Sierras, for example. So, okay, let's take a look at what we mean by an equipotential surface. An equipotential surface, sometimes just called an equipotential, this is a locus of all points, okay, all the points surrounding a charge distribution having the same electric potential. So here, okay, you can assume that these different, there's different closed lines, and each of them represents a different electric potential of the human heart. So what we're going to take a look at here are some properties of equipotentials, of equipotential surfaces, okay, and if in your notes, they're listed on the last page. So we'll state each property, okay, we'll give a brief proof of each property, and then try to look at some examples or applications of these properties. We're going to talk about a total of 6 properties of equipotentials, okay, of equipotential surfaces. The first 3 we will tackle in this slide. So the first property for equipotentials is that the potential difference between any 2 points on an equipotential surface is 0. Well, as we see, this really just comes from our definition of an equipotential surface, right? An equipotential or an equipotential surface, same thing. This is the set of all points on a surface that are at the same potential. So by definition, there is no difference in potential between any 2 points on that surface. We'll take a look at this. We're going to look at a simulation. We will combine all 3 of these properties on this slide, and in the next slide we'll take a look at a simulation, okay, illustrating these 3 properties. The second property we'll introduce here is this. The work required to move a charge along an equipotential surface is 0. Okay, well, again, from the definition, that should make sense. Remember that the electric potential difference between any 2 points is equal to the electric potential energy difference, okay, between those 2 points, divided by the charge which is moved between those 2 points. In other words, electric potential difference, okay, is equal to the energy difference per charge. And that energy difference, the definition of electric potential energy or electric potential energy difference, is defined as the opposite of the work done. So we can go from potential energy to work just by putting in that negative sign. Well, when you look at that definition, okay, we know that the electric potential difference, okay, between any 2 points on an equipotential surface is 0. That's property 1, okay, which therefore tells us that the only way that can be true if, okay, delta VBA is 0, okay, for a charge, then the work has to be 0. So here, important to know that you can move a charge along an equipotential surface virtually for free. It takes no work to do so. Okay, and like I said, we'll illustrate this with the simulation on the next slide. The third property here, a little bit more complicated, tells us that at any given point on an equipotential surface, the electric field is perpendicular to the surface. Let's see how this, okay, follows logically from our definition here. So starting with the definition of electric potential difference between 2 points, any 2 points A and B, okay, and you recognize that as the okay, line integral here. Okay, this is just the definition of electric potential difference. And here we can say that if A and B are points on the equipotential, okay, then we know that, okay, the electric potential difference between those 2 points on the equipotential must be 0. Okay, that is by definition of an equipotential. Well, let's think about this. So if the electric potential difference is 0, according to this definition, well, one possibility is that the electric field is 0 in that region. That could be, okay? But For cases where the electric field is not zero, okay, in a region where the electric field is not zero, the only other way that the integrand here can end up with a value of 0 is if cosine theta has a value of 0, which would imply then, okay, that theta would have to be 90 degrees. Well, what is theta? Okay, theta is really the angle between, okay, the electric field, okay, and that vector ds. That vector ds, that infinitesimal displacement vector, in going between 2 points on the surface, has to be parallel to the surface of the equipotential, which then implies that the field, the electric field, must be perpendicular to the surface. Okay, so that's the end of the proof, but I'm just going to say note here, we can look at this from another point of view as well, another perspective, saying, look, if the electric field was not perpendicular to the equipotential, okay, was not perpendicular to the surface, then that would imply that there is a component of the electric field that must exist right along the equipotential, call that E parallel, such that, okay, there would be a force, let's call it the parallel force, okay, which would equal, okay, the charge being moved times this, okay, electric field component parallel to the surface, which would imply that work would have to be done on the charge in moving it along the equipotential surface, but that would violate property 2. So another way to think about, okay, why at any point on the equipotential surface, the electric field must be perpendicular to the surface at that point. And again, to illustrate this, we'll take a look at the simulation on the next slide, okay, involving the parallel plate capacitor.
All right, folks, we are going to take a look at this simulation software to review some basic properties of electric potential and of equipotential surfaces. If you'll notice in the middle of the screen here, you see a positive point charge having a magnitude of 2 microcoulombs. And you'll see here that I am moving the arrow above this potential box. This shows you the electric potential at various points. Notice what happens when I move this hand closer to this positive point charge. You'll notice that the electric potential increases. And likewise, notice that as we move away from that point charge, the electric potential decreases and goes to 0. This is a basic property of electric potential. You know that for a point charge, the potential goes like Coulomb's constant times the magnitude of the charge, I should say just times the charge, divided by the distance between the charge and the field point. You'll notice that if we now take a look at a negative point charge, let's say if magnitude minus 2 microcoulombs, that when the hand moves closer to the negative charge, the electric potential increases in magnitude, but it is now negative, so it gets smaller. It would go to negative infinity right at the position of that negative point charge. As we move away from the negative point charge, the electric potential, well, technically increases, but approaches 0. So let's again take a look at a positive point charge. And what I'd like to do is to check the potential field box. These yellow concentric circles that you see represent equipotential surfaces for that point charge. I want you to notice that as I move my hand right along an equipotential surface, if you look at the electric potential box, you'll see that it is constant in magnitude. That is, its value does not change. It has a value of about 0.08 times 10 to the 5th volts. If I come in here and look at a different equipotential surface, you'll see that the value of electric potential is much bigger. It's 0.22 times 10 to the 5th volts. But once again, as I move right along that equipotential surface, you'll see that the value of the electric potential remains constant, okay, at about 0.22 times 10 to the 5th volts. This is a basic property of equipotential surfaces. all points on an equipotential surface are at the same electric potential. Let's come over here and check the electric field box, and you will now notice that these green electric field vectors are perpendicular to the equipotential surfaces. This again is a basic property of equipotential surfaces. The electric field should be perpendicular wherever those field lines cross the surface. If I come over here and we look at a different charge configuration, how about a configuration of 2-point charges, one having a charge of 2 microcoulombs, the other minus 2 microcoulombs, you will once again notice that wherever those field lines cross an equipotential surface, that they are perpendicular to the surface at that point. Another property of equipotential surfaces is that the electric field is strong where equipotentials are closely spaced and weak where they are far apart. Now you'll notice here, if you take a look at the strength of the electric field, that in this region right here, where the equipotentials are quite far apart, the field has a fairly small value, about 0.05 times 10 to the 5th volts per meter. Notice that if I bring the hand in over here where the equipotentials are much closer to each other, that the field strength gets much bigger. This is completely analogous to the contour lines on a map of elevation. Contour lines, you may recall, are spaced at even increments of elevation. So where those lines are close together on a contour map, that suggests that the elevation changes quite quickly. We can think of this by saying that when the lines on a contour map are close together, a large force is required to enable a person to make an elevation change quickly. In a similar way, we can say that where the equipotentials are spaced close together, the electric potential changes quickly, and thus a strong electric field is required to change the electric potential quickly in such a short distance. And lastly, we'll take a look at this simulation of a parallel plate capacitor to see another basic property of equipotential surfaces, and that is that the work required to move a charge along an equipotential surface is 0. In this simulation here, let me check the lines of force box. You can now see what the electric field looks like between the plates of the capacitor. I'm going to check the equipotential lines box, and you will see that these yellow equipotential lines are once again perpendicular to the field lines. Notice what happens here if I take this charge here, if I move it along an equipotential surface. Okay, you'll notice that the value of the force is constant, okay, and you will also notice that the direction of the force okay, at all points here is perpendicular, and you can see the direction of the force on the charge here, that at all these points here, the direction of that force is perpendicular to the direction that the charge moves. In such a case, the work done by that force, when the force is perpendicular to the displacement, the work done by that force is 0. This suggests that no net work is done when a charge moves along an equipotential surface. Now, you can see here that if I move that charge in the direction of the field, not only does the if I move the charge in the direction of the field, you see that now the direction of that force has a component in the direction of the displacement, in which case work is done in moving that charge.
The fourth property that we'll introduce here in this slide is one that was briefly mentioned in the simulation on the previous slide, but we will more formally talk about it here. And it goes like this. The electric field is strong where equipotentials are closely spaced and weak where they are far apart. In other words, there's this inverse relationship, okay, between electric field strength and equipotential spacing. And we will see briefly, shortly, how the analogy, okay, between electric potential and elevation on a contour map. So starting here with our definition of electric potential difference between 2 points here for a uniform field, and this is just a special case, but what applies here is generally true. We can say that since the electric potential difference is constant here for any 2 points on two given equipotentials, doesn't matter what those points are. Okay, take a point on equipotential 1, a point on equipotential 2. Okay, the difference in electric potential will be the same regardless of the 2 points you choose. So if that's constant, then just looking at the setup here, we can see that there is an inverse relationship here between electric field strength and delta S, where delta S is really a measure of the displacement, the magnitude being the distance between your two equipotentials. Looking at this in another way here, we know what we talked about earlier today. The electric field is, by definition here, when we look at a single coordinate here, is just the opposite of the derivative of potential with respect to the coordinate. You can think of this as a slope here, meaning that in a region where the gradient or the slope is large, that means where the potential changes, let's say, quickly with distance, that would suggest a region where the electric field is large. And again, we'll get to this. We'll see the analogy with a contour map shortly. So to see this visually, though, before we get to the contour map, let's look at electric potential. Let me show you an example here. Here's two equipotential surfaces, two equipotentials, and we're going to consider a few different points here. So given S1 and S2, if these are equipotential surfaces, and these 4 points A, B, C, and D, what we're saying is for the choice of any 2 points on these equipotentials, the difference in electric potential is going to be constant. It doesn't matter what 2 points you choose. So I'm saying here that the difference in electric potential between these 2 points here, A and B, will be exactly the same as the difference between these 2 points, D and C. And when we look at this, from our definition of electric potential difference here, what we can see here, if we consider average values in these regions for the electric field in this region here between C and D and between A and B, for average values, that field could be continuous and change, but on average, what we're saying is that the electric field here between points A and B, in this region, times delta S, really the distance between these 2 points, must be the same as the electric field in this region CD times the distance between those 2 points. So you can see here what this means. When the spacing is close, when that distance is small, that suggests the electric field is pretty large. In other words, it means that you need a pretty large electric field in that region to be able to change the electric potential, in a relatively short distance, in a short amount of space. And if we think about the analogy, of a contour map, it's very helpful because you may be more familiar with that. Now, contour maps, help us understand elevation. And what we can say is that contour lines are spaced at even increments of elevation. So just as we can say that on an equipotential, any 2 points on that equipotential have the same electric potential, we can say that on the contour line on a contour map, any 2 points on that contour line have the same elevation. And think about what this implies. Okay, when the elevation changes quickly on a contour map, okay, where you have a steep slope, okay, a steep hill, this is where lines are close together. This suggests that a large force is required to enable that elevation change to occur quickly. So in a region on a contour map where the contour lines are close together, that suggests a steep gradient, a steep hill, so to speak, in which case a lot of work must be done to move from one contour line to another. In the same way, we can say that, okay, in a region on a map of electric potential where you see these equipotentials plotted, okay, if the electric potential changes quickly, okay, where that's going to happen when these equipotentials are close together, that would suggest that you must need a strong electric field in that region, okay, in order to bring about the quick change in electric potential. And to move a charge, okay, from one location to another requires a fairly big force and a big electric field and a big amount of work, okay, if those equipotentials are closely spaced in that region. So these last two properties of equipotential surfaces, okay, pertain specifically to the case of conductors in electrostatic equilibrium. And I just want to remind you, if you remember back to our lecture, okay, we did an entire lecture on conductors in electrostatic equilibrium, and we stated the various properties of them. And we'll revisit some of these properties here in this slide because they'll enter our form of proof. Do you remember, though, that the very last property we stated without proof? We said that for an irregularly shaped conductor, okay, that the surface charge density would be greatest in locations where the radius of curvature was smallest. And if you remember, okay, you wrote it down, you stated it. I showed this to you experimentally, but we did not give a proof of it, and I told you the proof would come later. Well, guess what? Okay, it's now later. So before we can get to property 6, we need to state property 5 and give a proof here. Turns out that a conductor in electrostatic equilibrium is an equipotential. It is an equipotential surface. And we can see this very simply from our definition of, okay, electric potential difference. Remember that the first property we talked about for a conductor in electrostatic equilibrium is that the electric field is 0 at all points inside that conducting medium. Okay, and if the electric field is going to be 0, then from our definition of electric potential difference, if we consider the difference in electric potential between any 2 points within that conductor, okay, then if the electric field is 0 for all points in that conductor, okay, inside the conductor, then that implies that the electric potential difference between those 2 points is 0 as well. Okay, which means that if there's no difference in electric potential between any 2 points inside of that conductor, then that means that all points inside the conductor are at the same electric potential, which means it's an equipotential. It's an equipotential surface. Okay, so there is property 1. Now, this is the second property involving conductors in electrostatic equilibrium, what I'm calling here equipotential surface property 6, okay, goes like this. And I'm stating it a little bit differently, but it gets at the same basic idea. At the surface of a conductor, okay, conductor in electrostatic equilibrium, okay, the surface charge density and electric field are greatest where the radii of curvature is the smallest, is the least. So let's take a look at a proof for this. So we're going to consider 2 isolated spherical conductors, and they must be isolated so we can treat them as separate objects with distinct radii of curvatures. We could look at a single object that is uh, okay, irregularly shaped, an irregularly shaped conductor where the radii of curvature for the single object varies, that applies too, but we're going to let's just make this easier. Let's look at two distinct conductors with different radii, R1 and R2, but they're going to be electrically connected, which means that both of them will be at the same electric potential. Okay, so let's look at a picture of these two conductors. And since the spheres are connected by this conducting wire, they are at the same electric potential. Okay, because we just said that, okay, all points on that conductor in electrostatic equilibrium are the same potential. So whatever the potential of one of them is, it must be the same as the other one if they're connected by a piece of conducting wire. And here, okay, we can say that the electric potential for the spherical charge distribution matches that of a point charge. We can write it as, okay, KQ1 over R1 equals KQ2 over R2, where we're looking at the potential, electric potential on the surface of the sphere, right? If we go inside of that sphere, okay, okay, then we know that if it is a charged sphere, that one of the properties we learned for conductors is that any excess charge must reside on the surface of the sphere. So this is why we're looking at the surface of the sphere where the excess charge is. If you look inside of that sphere, okay, there won't be any charge. So at the surface of the sphere here, this is the expression for electric potential. Okay, K times the charge which resides exclusively on the surface, Q, okay, divided by the radius of that sphere. Now, okay, the charge on the surface is simply the surface charge density times the surface area, okay, by definition of charge density. And for a sphere, we can write the area of the surface to be 4 pi r squared. So making this substitution, okay, into our definition here, okay, of the electric potential at the surface, making the substitution here, and simplifying, okay, we end up with this very simple result here, okay, sigma 1 times R1 is equal to sigma 2 times R2. And what this tells us then is that, okay, there is this inverse relationship that exists between, okay, the surface charge density and the radius of curvature. Okay, where the radius of curvature is large, the surface charge density is small. Okay, and where the radius of curvature is small, the surface charge density is large. Okay, and this is an important physical concept that has applications in technology here. And I'll show you not a real one, but a model of an electrostatic precipitator. So these electrostatic precipitators can be used to filter air in your home. That is a common method. Some of them simply use, okay, material filters, but others actually use, okay, charged plates to basically, take the dust and dirt out of the air. And I'll also show you an example of, okay, the corona discharge here. That happens from a point. Okay, pointed objects have a very small surface charge density, which means the electric field at a point would be very strong. Okay, and that's what I will illustrate, okay, with the next couple of slides. We say that the surface charge density and the electric field at the surface of a charged conductor are inversely proportional to the radius of curvature of that conductor. In other words, okay, where you have a conductor that has a small radius of curvature, like a sharp pointed object, okay, the electric field and the surface charge density there should be very strong. And we're going to try to show that this is the basic principle behind the electrostatic precipitator. Electrostatic precipitators are used in home air purifiers, And they're also used in coal-fired power plants, okay, to be able to safely get rid of these combustion products. The combustion products are actually going to be attracted to the sharp points of a charged conductor. So you can see here in this one that we're going to model today, we've got a chamber here, and we are going to start by putting some smoke in there, okay, with this incense here. And you'll notice that after we collect some smoke in there, that on the sides here I've got these two nails, and at the surface here, okay, the radius of curvature is very small, as you can tell by the sharp point. So once we fill this chamber here with smoke, okay, we will then connect these nails to opposite sides of the Wimshurst generator here, and we're going to produce a powerful electric field. And these smoke particles in here, okay, should start to move opposite the direction of the field, okay, when the field exists. So here goes. Let's crank this thing up, generate a strong electric field at those points, and you'll see what happens to the smoke particles. Here is yet another demonstration that nicely illustrates this inverse relationship between the surface charge density and electric field at the surface of a charged conductor and the radius of curvature of that charged conductor. So you see here in this demonstration we have two conductors, one in the form of this nail, okay, which when you look at the radius of curvature of the tip is extremely small, okay, because of the point. And we would expect that when we charge it up, the surface charge density and the electric field there should be very large. On the other hand, we have this flat disc, which essentially has an infinite radius of curvature, where we could say that the electric field and the surface charge density should be extremely small, okay, very close to zero. So when we charge these conductors here, we will get an electric potential difference between them, okay, and you're going to see evidence of the electric field when we light this candle here. Okay, these combustion products that are now rising vertically will get polarized in this field and will start to move okay, in this field, and you will see the effect in the form of a wind, okay, that affects the candle flame here. So while electric fields are omnipresent, okay, they're hard to see, but in this case here we're seeing the effects of the electric field set up between these charged conductors.